We're going to talk about some other voice synthesis techniques, including FOF, vocoders, Macaulay-Quartieri, and SMS. Starting with FOF. FOF is a French acronym for Formant Wave Function Synthesis. And FOF is very much a descendant of VOCEM. VOCEM was designed to approximate the response of a resonance to a pulse, and FOF can be looked at as just a little bit more accurate model of that. It uses a sinusoid instead of sine squared. It uses continuous exponential decay instead of this pulse decay factor. So it could be viewed as a little bit more realistic or accurate modeling of a resonance. It does have a couple of things that are a little bit ad hoc. There's a rise time associated with each FOF pulse, and the FOF pulses are not infinite in length, and so that's part of the approximation. Unlike VOCEM, the FOF pulses can actually overlap one another, which is a more accurate superposition of what happens when you put pulses into a resonance. In the frequency domain, the FOF pulses look like this. There are actually a variety of curves. You can have a very narrow resonance where the center frequency is the frequency of that sinusoid that's being exponentially damped. As you change the rise time, which is a little added feature, you can increase this dimension, which is called the skirt width, and also you have a very variable attenuation, which controls the bandwidth of the resonance. FOF parameters can be obtained automatically by modeling the peaks of a short-time Fourier transform, and FOF is therefore not limited to voice synthesis. It's just a way of creating resonances and adding them together. FOF synthesis works like this. First of all, we create virtual impulses according to the frequency of the input source. And for each one of these pulses, we create the response, which includes a rise time and an exponentially decaying sinusoid. And that's essentially a grain which completes the signal. And because these grains can overlap, as you see over here, when the pulses get closer together, the decay time might be so large that there's overlap. So in terms of programming, these FOF generators have to be dynamically allocated and for each pulse and freed when the pulse completes, and we just sum up all of the actively running pulses. We can simulate multiple formants by just running multiple FOF generators at the same time, and we take the sum of all the grains as the output. I have a sound example for you. This is one of the most famous uses of FOF. This goes back to 1983. It's a real tour de force of FOF synthesis created by Jean-Baptiste Barrière. That here can play just a little bit of that. So you hear some granular synthesis type sounds and different rhythms. Those are not necessarily characteristics of FOF synthesis. You can also use FOF synthesis to make long sustained tones, but those vocal qualities that you hear are definitely created by the resonances that FOF simulates. Another technique used for voice synthesis and voice processing is the vocoder. So here's a picture of what a vocoder looks like. You have a filter bank. So these filters represent all of the potential resonances. So usually there are many channels of filters at different frequencies. Vocoder includes analysis and synthesis. So what's happening here is we use a modulation signal, or maybe you could say this is the signal that we are analyzing. And we filter that modulation at all these different filter frequencies and use an envelope follower to measure the amount of energy that comes out of the filter. So in a sense, this is kind of like a Fourier transform. We have at each frequency, we're measuring how much energy there is. And then for the synthesis part, we put any kind of carrier into the vocoder. So for example, this could be a pulse train. It could be other sounds, synthesized tones. And we separate that carrier frequency or the source signal into the same bands using the same filters, and we scale it according to the energy that was in the signal that we analyzed. And we sum up all the bands and we get output. The phase vocoder is an enhancement of the vocoder. It's intended mainly for sounds without too many partials. And the idea of the phase vocoder is we assume that each partial of the signal lands in a separate discrete Fourier transform bin, or think of that as filter channels or different frequencies. But if these partials are well separated, then the Fourier transform can accurately analyze each partial. And so what the phase vocoder does is takes each partial and estimates the amplitude and phase of the partial, and then it does a reconstruction using an inverse fast Fourier transform. The reason phase is important is when you do reconstruction, you can stretch the spacing of the frames, which puts the frames farther apart, which means the phase is going to change. And the phase vocoder actually does correction of the phase to reconstruct the partials as if they were taking more time. So here's some examples of the phase vocoder. Here's an original signal.
This is a recording for the Music and Computers book. This is a recording for the Music and Computers book.
So that was obviously stretched. Then we can also speed up and then slow down the sample rate to change pitch.
This is a recording for the Music and Computers book.
In some sense, a generalization of the phase vocoder is Macaulay-Quartieri synthesis. MQ synthesis is an additive sinusoidal model. So just like in phase vocoder, where we were trying to separate all of the partials, analyze them, the frequency, amplitude, and phase, and reconstruct them, well, Macaulay-Quartieri takes a sound and breaks it down into sinusoids by tracking the peaks in the spectrum and trying to estimate how these sinusoids change in frequency and amplitude and phase over time. The signal is essentially represented as a list of trajectories of sinusoidal partials, and then to resynthesize, you just add them together. Time stretching and frequency shifting are easy given the sinusoidal models. There is no buzz or artifacts running at the frame rate, which often happens with vocoders and phase vocoders. The drawbacks are noise is handled by large numbers of sinusoids. It's not efficient. It's not flexible. Resonances are not modeled by MQ. analysis synthesis. And so if you're trying to do a source filter model, this is not the way to do it. And there's no obvious cross-synthesis method. So, for example, taking vowel sounds from one source and the source signal from another source. Nevertheless, I'm talking about MQ analysis and synthesis here because it was developed as a representation of speech and a way of encoding speech. And also, MQ is very close to the final method we want to look at, which is spectral modeling synthesis, or SMS. SMS started as Xavier Serra's thesis work at Stanford. He continued this work in the music technology group at Pompeu Fabra University in Barcelona, where there's a very large group doing work on computer music and music information retrieval and other topics. So SMS is and can be viewed as an extension of Macaulay-Quartieri analysis, where the extension adds an explicit model for noise. This is a picture of what SMS looks like. This is from Xavier Serra. It looks kind of complicated, so let's take this one step at a time. When we do the analysis, sound comes in, and we do a windowed FFT. We'll ignore some details about the analysis and just say, we're taking FFTs, we get the magnitude spectrum, the phase spectrum, and we do peak detection on the spectrum. So in other words, what's a peak in the spectrum? It means a sinusoidal partial. And from these peaks, we can do pitch detection to figure out the fundamental frequency. And we have a set of spectral peaks. So from frame to frame, we are trying to track these peaks, assuming that those peaks are actually the result of sinusoidal partials. So like Macaulay-Quartieri, we're tracking these peaks and building a trajectory of each peak or each partial over time. Then what's new with SMS is we take this information and we reconstruct, or we resynthesize the sound in terms of these sinusoids. Then we look at the difference between this reconstructed signal and the original signal. That leaves a residual, which normally will be noise-like, because if it were sinusoidal, then it would show up as a peak in the spectrum. So what's left is everything else, non-peaks, which are kind of noisy. And so then there's a curve fitting process that approximates the shape of the residual spectrum. And from that, the coefficients are output, and that's part of the representation. So now we have two parts. We have the sinusoidal part and we have the noise part. We can do some interesting things with that. Here are some examples, again, from Xavier's work. And let's start with an original signal that to be analyzed. So you notice that's a pretty tonal piece. It's a guitar, but there's some interesting noise as the fingers are sliding across the strings. So the sinusoidal part is also called the deterministic part. And so we can resynthesize only the deterministic part of that signal. So the noise and the sliding are gone, but the tone is there. This is the noise part. And we can resynthesize everything, but it's so close to the original. Let's just go on to some interesting transformations. So here, obviously, the sinusoidal tracks have been transposed down. There, the sinusoidal tracks have been stretched to inharmonic ratios. And by the way, try to figure out for yourself what's going on here before I tell you. It's a very interesting kind of listening test, and test of your knowledge about synthesis and what's going on in sounds. So I think that's pretty clear that the original pitches were all transposed down or up to the same pitch. So obviously, if you can transpose notes, you can make new melodies. And so also you can change pitch continuously. You can also take these sinusoidal tracks and warp them in time to make them go faster or slower. So that's slower, some time stretching. It's interesting to me listening to the time stretching because the guitar sounds sound pretty good to me. The noise components, the attack and the slides and so on, don't sound so natural because when we hear, we expect the noise coming out of a guitar playing to be kind of instantaneous based on plucking, and we never hear noise stretched out. So that's, I think, why it sounds a little less than natural. So I think that was some time stretching and also some some frequency warping to get more metallic inharmonic sound. So those are some examples of playing with sinusoidal and noise models in SMS.